Today, we're going to talk about what might just be the next great leap for artificial intelligence. We're going to move beyond just asking how we make AI bigger, and instead ask, how do we make it fundamentally, well, smarter?
I mean, we've all seen it, right? The current crop of AI is just astonishing. It can whip up these incredible images from a simple text prompt, it can write really complex code, and it can answer questions by pulling from, basically all of human knowledge. It really feels like we're talking to a whole new kind of intelligence.
And that brings us to the million-dollar question. When an AI spits out an answer, is it actually understanding the concepts behind it? Or is it just the world's most sophisticated pattern-matching machine? Is what we're seeing true cognition?
To get to the bottom of that, we really have to look under the hood. Because behind this amazing magic show, the very architecture of modern AI is starting to run into some serious, fundamental problems. You could call them cracks in the foundation. And they suggest that just making these models bigger and bigger isn't going to be the answer.
Yeah, the argument here is that these aren't just little bugs we can iron out later. Nope. These are critical bottlenecks that are basically putting a hard ceiling on AI's potential to ever be genuinely intelligent. Let's break down the three biggest ones.
First up is the absolutely staggering energy cost. Okay, so the human brain, the most complex thinking machine we know of, it runs on about 20 watts. That's less than a dim light bulb. Now, compare that to training a big model like the new Llama 3.1. It burns through an unbelievable 25.3 million watts. That is just, it's not a sustainable way to grow. And all that power consumption, it has a massive environmental footprint. Training that one model pumped out almost 9,000 tons of CO2. Just to put that into perspective for you, the average American's yearly carbon footprint is around 18 tons. So the computational cost here is quickly becoming a real environmental problem.
Okay, so that's the second bottleneck. And honestly, this one's even more fundamental. It's not about physical limits anymore, we're talking about cognitive ones. It turns out that an AI can get superhumanly good at a very narrow task while completely, utterly failing to grasp the actual point of what it's doing. And this quote just illustrates the problem perfectly. In one study, researchers trained AI agents to run through a maze and pick up a coin, and they got incredibly good at it. But then, during the test, the researchers moved the coin, and what did the AI do? It just ignored the coin completely and ran straight to the end of the maze. See, it had learned the movements, the patterns, but it never learned the actual goal. It mastered the how without ever understanding the why.
This whole thing has a technical name, goal misgeneralization. But what it really boils down to is this. The AI becomes an expert at copying the patterns it saw in its training data, but it fails to build a solid internal model of what it's actually supposed to be doing. It's all performance with zero comprehension.
And the third bottleneck is how incredibly data-hungry these systems are. Let's take the game of Go. AlphaGo, the AI that famously beat the world champion, it trained on what amounts to over 100 million games. A human grandmaster, they get to that same elite level after playing maybe 50,000 games in their entire life. The AI needs thousands of times more data to learn the same skill.
So if the current AI blueprint is this flawed, where on earth do we find a better one? Well, the answer might actually lie in the original thinking machine, the one that solved all three of these problems millions of years ago.
Look, the human brain isn't perfect, not by a long shot. But it is, without a doubt, the best example we have of an intelligent system that is super efficient, that understands goals, and that learns from a surprisingly small amount of data. It's the ultimate proof of concept.
And let's just circle back to this number because it is just so important. All of that creativity, all that planning and learning and everything else, it happens on just 20 watts of power. This incredible efficiency is a giant clue that we're probably missing something really fundamental in how we design our AIs.
And this brings us to a proposed solution, a brand new blueprint for AI architecture, one that's inspired directly by our own brains. It's called the dual-loop architecture.
So how in the world does it work? Well, imagine a system that has two parts that are constantly talking to each other. You have a fast inner loop that's dealing with the here and now, reacting to the world in real time. And then you have a slower outer loop that takes all those experiences, thinks them over, and stores them in memory to build abstract ideas and long-term plans.
Now, if this is starting to sound familiar to you, it should. It maps almost perfectly onto those psychological concepts of System 1 and System 2 thinking. That inner loop, It's like our fast, intuitive gut reaction system 1. And the outer loop is our slow, deliberate reasoning system 2. The big idea here is to actually build an AI that has both of these systems and lets them work together.
Okay, that might sound a little bit abstract, I get it. So let's make it really concrete with a super simple example. The act of learning how to reach for a cup of coffee.
Let's walk through this. It all kicks off with a goal. I want that cup of coffee. That simple desire immediately activates the inner loop. Its job is all about fast, real-time motor control. The tiny muscle movements, the visual adjustments, the raw physical action of just reaching out. Now, once you successfully grab that cup, that entire experience, all the sensory data, all the motor commands, gets passed up to the outer loop. And this is where the real learning happens. It takes that successful action and locks it in. But here's the magic trick: abstraction. The outer loop doesn't just save a memory of how to grab that specific coffee cup on that specific table. No, it creates a general, abstract concept of reaching. And that's how we go from one single action to a flexible, reusable skill that we can apply to grabbing a pen, or using a new tool, or even planning a whole complex series of actions in the future.
So, why does this all matter so much? Because adopting this kind of architecture could fundamentally change the entire direction of AI development. It could solve the very problems that we started out with. A system built like this promises a future with AI that's far more human-like. It would be way more energy efficient because it would use its heavy-duty thinking strategically, it would learn with real goal-directed understanding, it would generalize skills to totally new situations. But maybe most importantly, it wouldn't just be mimicking patterns anymore. It would be actively building and refining its own internal model of how the world actually works.
So, the really crucial takeaway here is this massive paradigm shift. The goal is no longer just about scaling up, about building bigger and bigger, more power-hungry models. It's about designing smarter, more elegant blueprints for intelligence itself.
And that really leaves us with one final question to think about. As we keep chasing this dream of artificial general intelligence, is the best path forward really through brute force and just building bigger machines? Or is it through smarter design and better blueprints, inspired by the most efficient thinking machine we've ever known?